Hi, my name is Bailey Chambliss, and this is my Physics 2211 Video Lab Report number 1, Constant Velocity. The purpose of this lab is to observe the actual versus predicted position of an object moving at a constant velocity using a glow script model of perfect conditions and a tracker model of the actual conditions. The first fundamental physical principle used in this lab is Newton's first law. This states that an object at rest remains at rest, and an object in motion remains in motion at a constant speed and in a straight line unless acted on by an unbalanced force. As shown in the figure below, an object with a net force of 0 will remain at a constant velocity, while an object with a net force non-zero will experience an increase in velocity. The second fundamental principle used in this lab is Newton's second law, or the momentum principle. This states that the acceleration of an object depends on the mass of the object as well as the amount of force applied to the object. With this, we can derive the position update and velocity update formulas, both of which will help us in our predictive computational model. The position update formula states that the final position of the object is equal to the object's initial position plus the average velocity of the object times the change in time. The velocity update formula states that the final velocity of the object is equal to the initial velocity plus all of the net forces acting on the object divided by its mass times the change in time. So a brief preview of our results. In comparing the glow script model of ideal conditions to the tracker model of the actual results, the models shared a very strong resemblance, suggesting that the system under investigation was moving at a constant velocity. Both the glow script model and the tracker model had a linear shape with positive slope, indicating constant velocity. The first model used in this experiment was the tracker model of the actual object. In this, the system would be the cylindrical object, our surroundings are everything around the object, and the assumptions made are that friction and air resistance are negligible. We have our original video, as well as the video added to the tracker platform. Our next model is the glow script model, which uses our initial conditions, calculated below, as well as the velocity update and position update formulas in order to predict the position of the object in ideal settings. Our position update formula can be seen in the code as ball.position equals ball.velocity times delta t, while our velocity update formula can be seen as ball.velocity equals ball.velocity plus F net divided by ball times mass times delta t. In comparing the results of the glow script model to the tracker model, these two models were very close to one another. This means that in our tracker model, we were able to create a near ideal environment, but some deviances in results may come from friction, air resistance, and other human error. What if? So what if the axes were flipped? Because the choice was made in the tracker model for the change in position to go in the positive x direction, by changing the axes, we are simply changing the sign of the slope of the graph, not the magnitude of the slope. Therefore, we would still come to the same conclusion. What does it mean? Is it possible to determine how many pushes and pulls are added together to give a net zero force in this case? In the computational model of this experiment, the net forces were set to 0, although in real life, this may not be the case. Factors such as those suggested before can cause deviances from the predicted model. In short, it is difficult to determine the exact number of forces acting on an object and the magnitude of such forces. Thank you.